Hello and welcome to the lecture 2 of this lecture series on complex number. In this lecture we are going to learn polar representation of complex number. Let z be a complex number, so I can write this z as z is equal to a plus ib, can be written as ordered pair ab. In a complex plane, z can be represented by a point whose Cartesian coordinate is this ordered pair ab. So let me make the complex plane. This is the two axes. One is called the real axis, x-axis, and this axis is called the imaginary axis, y-axis. So let P be the point. P is a point whose Cartesian coordinate is AB. Now we are taking this origin as a pole and this x-axis as initial line. Let r theta be the polar coordinate of the point AB. The same point P, the polar coordinate be r theta. So that means the radius vector through the origin to the point P will make angle theta with the initial line, and the distance OP is r. So r theta is the polar coordinate of the point P. Now drop a perpendicular from P to the real axis OX. Let this point be PQ. Then we know that this OQ is equal to A. This is A, and QP is B. This is B. Now in triangle OPQ, OQ by OP is equal to cos theta. Base by hypotenuse is equal to cos theta. So OQ is A and OP is R. So it is equal to cos theta. So A is equal to R cos theta. So we get this relation, A is equal to R cos theta. And again from the same triangle, PQ by OP is equal to sin theta, that is perpendicular by hypotenuse. PQ is B, OP is R again, is equal to sin theta. This implies B is equal to R sin theta. So again we get this relation, B is equal to R sin theta. The distance R, this distance R is the distance of a point AB, distance of the point AB from the origin. Coordinate of origin is 0, 0. So the distance R is equal to OP is equal to under root of A minus 0 whole square. That means A square plus B minus 0 square B square. So R is equal to plus under root of A square plus B square. This R is positive because R is a distance. This R is called the modulus of the complex number Z, and R is equal to plus under root A square plus B square. For every complex number other than 0 complex number, R is greater than 0. Since R is a distance, so it is always greater than 0. But for a 0 complex number, R is equal to 0. So 0 complex number can be written as 0, 0 in order pair form. So if you put A is equal to 0, B is equal to 0, then r is equal to under root of 0 square plus 0 square is equal to 0. You will get the value 0. Thus, every non-zero complex number has a positive modulus. The angle theta made by the radius vector through the point AB with the real axis is called the argument of the complex number or amplitude of the complex number z. So this angle theta, this is the angle theta made by this radius vector from the origin. This is a point P whose polar Cartesian coordinate is AB and the polar coordinate is r theta. We have already discussed. So this theta angle made by this radius vector through the point AB with the initial line is called the argument or amplitude of the complex number z. So z is equal to a plus ib. So a is equal to r cos theta. We have already derived this, r cos theta, and b is equal to r sin theta. So if you take r outside, cos theta plus I sin theta, so we are getting z is equal to r into cos theta plus I sin theta. This representation of the complex number z is called the polar representation of the complex number or polar form or normal form of complex number. So this theta cannot be determined for a zero complex number. So therefore, zero complex number has no polar representation. You can see from the figure, this theta is the argument of this complex number z. But if I measure this angle theta like this, this will be 2 pi plus theta, 2 pi plus theta. This is also the argument of the same complex number. Now if I continue this process, I will get another argument like this. If you do like this, this is 4 pi plus theta. So this theta has infinitely many value and differing from one another by the angle multiple of 2 pi. The value of theta is expressed by argz or ampz, argument of z or amplitude of z. Suppose alpha be the value of theta, that's satisfying the relation a is equal to r cos theta, b is equal to r sin theta. Then argument of the complex number z can be written as alpha plus 2n pi. Argument of z can be written as alpha plus 2n pi. Because as we just know that this alpha has infinitely many value, so differing by the multiple of 2 pi. So when you run the value of n, 0 plus minus 1 plus minus 2, you will get the different value of the argument of z. If the value of theta lies between minus pi to pi, that is theta minus pi less than theta less than equal to pi, then this value of theta is called the principal value of the argument. We will denote it by small argz or ampz, argument of z, amplitude of z. Amplitude of complex number is to be determined from the relation a is equal to r cos theta, b is equal to r sin theta simultaneously, not from the relation theta is equal to tan inverse b by a. So the value of theta must satisfy both the relation a is equal to r cos theta, b is equal to r sin theta. Here we are going to find the modulus of a complex number z, argument of z, and express z in the polar form, where z is equal to minus 1 plus I. Let minus 1 plus I is equal to r cos theta plus I sin theta. Let r cos theta plus I sin theta be the polar representation of this complex number minus 1 plus I. Then I can equate this real part and imaginary part. Then I will get r cos theta is equal to minus 1. This is the real part, r cos theta is equal to minus 1, and the imaginary part is this r sine theta. This r will multiply with this sine theta, so we will get r sine theta is equal to the coefficient of I, that is 1. R sine theta is equal to 1. Now as we know that the complex number z is equal to minus 1 plus I, the modulus of z, that is r, is equal to under root of minus 1 square plus 1 square is equal to root over 2. So that means r is equal to root over 2. So we got this value of r over here. R is equal to root over 2. Now I can put this value of r here and here. So we will get cos theta is equal to minus 1 by root 2 and sin theta is equal to 1 by root 2. Now from these two relation we will get the value of theta. So as we know that cos theta is equal to minus 1 by root 2, this implies minus 1 by root 2 is minus 1 by root 2 is cos 45 pi by 4, and cos pi by 4 can be written as cos of pi minus pi by 4, because cos of pi minus theta is equal to minus cos theta, and this will give you cos of 3 pi by 4. Now from the relation sin theta is equal to 1 by root 2, 1 by root 2 is sin pi by 4, and sin pi by 4 can be written as sine of pi minus pi by 4. So this is equal to sine of 3 pi by 4. So from this both the calculation, cos theta is equal to cos 3 pi by 4, that means theta is equal to 3 pi by 4. Sin theta is equal to sine of 3 pi by 4, that means theta is equal to 3 pi by 4. From the both this relation we are getting theta is equal to 3 pi by 4, so the value of theta is 3 pi by 4. Now we got the modulus of the complex number z. The value of r is root 2, that is modulus of the complex number z is equal to root 2, and the argument of z is 3 pi by 4. Now I can put this value of r and theta here in the place of r and theta. We'll get the polar form of the complex number z. So the polar form is r, I am replacing r by root 2 cos theta plus I sin theta, where theta is equal to 3 pi by 4. Next is some important complex number and their polar form with principal argument. Number 1 is 1. 1 is also a complex number. I can write 1 is equal to 1 plus 0 I. So the polar form of 1 is cos 0 plus I sin 0. Here the modulus of 1 is 1 and argument is 0. Next is I. The polar form of I is cos pi by 2 plus I sin pi by 2. So you know that cos pi by 2 is 0 and I sin pi by 2 is 1, so you'll get I. Here the modulus is again 1 and the argument is pi by 2. Next is minus 1. Minus 1, polar form of minus 1 is cos pi plus I sin pi. Modulus of this minus 1 is again 1 and argument of minus 1 is pi. And the fourth one is minus I, and the polar form of this complex number is cos of minus pi by 2 plus I sin minus pi by 2. Here the modulus again 1 and the argument is minus pi by 2. So these are some complex number with their polar form with principal argument. Here we are going to find the argument of the complex number z is equal to 1 plus I tan 3 pi by 5. So this complex number is given in the form of a plus ib form, where a, this is the real part, or this is the imaginary part. So if you find the modulus of this complex number, then mod z r is equal to mod z will be under root 1 square plus tan square 3 pi by 5. So here you will get this equal to under root sec square 3 pi by 5, and this equal to minus sec 3 pi by 5. I am taking this negative sign because sec 3 pi by 5 is negative, so that negative and this negative will make it positive because r is a distance, so it is always positive. Let the polar representation of this complex number be r cos theta, r sin theta. Then I can equate the real part and imaginary part. Here real part is 1 and here the real part is r cos theta. So r cos theta is equal to 1, and the imaginary part is here tan 3 pi by 5, and here the imaginary part is r sin theta. So r sin theta is equal to tan 3 pi by 5. Now r square is equal to 1 square plus tan square 3 pi by 5, that we have already done, and which is equal to sec square 3 pi by 5. That means r is equal to minus sec 3 pi by 5, because I already told you that sec 3 pi by 5 is less than 0. Putting this value of r in 1, we will get cos theta is equal to minus cos 3 pi by 5. So here you have to put the value of r. So when you put the value of r here, so it will be cos theta is equal to 1 by r, which is equal to 1 by r means minus sec 3 pi by 5, and this will be minus cos 3 pi by 5. So you are getting this result over here. Similarly, if you put the value of r in this relation, you will get sin theta is equal to minus sin 3 pi by 5. Now minus cos 3 pi by 5 can be written as cos pi plus 3 pi by 5, because cos pi plus some angle will be negative of that angle, and sin theta can be written as minus sin 3 pi by 5 will be equal to sin pi plus 3 pi by 5. So from this both the relation, theta is pi plus 3 pi by 5, and here also theta is pi plus 3 pi by 5. So our argument theta is pi plus 3 pi by 5. So you can see from here that this value of theta is greater than pi, so it is not a principal amplitude. To be a principal amplitude, the value of pi must be between pi and minus pi. That means the value of theta must be between pi and minus pi less than theta less than equal to pi. So here theta is greater than pi, so but the argument of z always lies between principal argument of z rather pi arc z pi. So this is the range of the principal argument. Here theta does not give the principal argument in our case, so our principal argument will be theta plus 2k pi. We have to choose this k in such a way that this argument lies within this range. So if I take k is equal to minus 1, then argument of z will be pi plus 3 pi by 5, and this portion will be, if I take k is equal to minus 2 pi. When you solve this, you will get argument of z is equal to minus 2 pi by 5. So this is the principal argument. Theorem related to argument of complex number. Suppose z1 and z2 be two complex number, non-zero complex number whose argument is theta 1 and theta 2 respectively. Here the theta 1 and theta 2 may not be the principal argument. If you multiply z1 and z2, then their argument will be theta 1 plus theta 2. But this theorem does not hold in general. If I take the principal value of the argument, then this theorem will not hold. Next theorem is again z1 and z2 be the two non-zero complex number whose argument are theta 1 and theta 2. Here the theta 1 and theta 2 may not be principal argument, it could be any argument. So theta 1 minus theta 2 is the argument of z1 by z2. Here also this theorem does not hold in general if I take the principal value of the argument. next theorem is for the principal argument. If Z1 and Z2 be two non-zero complex number, then the argument of Z1 Z2, that means this is the principal argument of product Z1 Z2, is the argument of Z1 plus argument of Z2 plus 2k pi, where when k is equal to 0, you will get the argument Z1 plus Z2 is equal to in this range, and when k is equal to 1, argument of Z1 plus Z2 will be less than minus pi, and k is equal to minus 1, argument of Z1 plus Z2 is greater than pi. Now next theorem is for the argument of this Z1 by Z2. If you have two non-zero complex number, then argument of Z1 by Z2, here this is the principal argument, it will be argument of Z1 minus argument of Z2 plus 2k pi, where this k is an integer. If I take k is equal to 0, then the argument lies in this range. If I take k is equal to 1, argument lies in this range. That means argument will be less than minus pi, and if I take k is equal to 1, argument will be greater than pi. If I prove this theorem, then you can prove theorem 1, 2, 3 yourself. Let Z1 be the complex number whose polar form is r1 cos theta 1 plus I sin theta 1, and Z2 is the complex number whose polar form is r2 cos theta 2 I sin theta 2. Here theta 1 and theta 2 are the principal argument. That means it lies between theta 1 lies between minus pi to pi, and theta 2 also lies between in this range. Here argument of Z1 is theta 1 and argument of Z2 is theta 2. These are principal argument. Now Z1 by Z2 is equal to R1 by R2 cos theta 1 minus theta 2 plus I sin theta 1 minus theta 2. So we can find this Z1 by Z2 is equal to R1 cos theta 1 plus I sin theta 1 divided by R2 cos theta 2 plus I sin theta 2. I'm going to multiply this numerator and denominator by cos theta 2 minus I sin theta 2. So it will be R1 R2 cos theta 1 plus I sin theta 1 into cos theta 2 minus I cos theta 2 minus I sin theta 2. So denominator will be cos theta 2 square plus sin square theta 2, which is equal to 1. So it will be R1 by R2, R1 by R2. Now if you multiply this, it will be cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. So it will be plus sin theta 1 theta 2 plus I cos theta 1 sin theta 2 plus sin theta 1 cos theta 2. So this will give you R1 by R2. I think this will be minus cos theta 1 minus, yeah. So this will give you R cos theta 1 minus theta 2 plus I sin theta 1 minus theta 2. So we got this result here. Okay, now this theta 1 minus theta 2 is the argument of this complex number Z1 by Z2. This is the polar form of the complex number Z1 by Z2. So its argument is theta 1 minus theta 2, but this may not be the principal argument. The principal argument of Z1 by Z2 will be theta 1 minus theta 2 plus 2k pi, where k is the integer, such that minus pi less than theta 1 minus theta 2 plus 2k pi less than theta 2. We have to choose this k in such a way that the value of this argument will lies between this range. But we know that this theta 1 minus theta 2 lies between minus 2 pi to 2 pi, because we have considered this theta 1 as a principal argument and theta 2 as a principal argument. So three case arises. That means when this principal argument theta 1 minus theta 2 lies between it could be less than equal to pi minus 2 pi less than theta 1 minus theta 2 less than equal to pi, or next case is minus pi less than theta 1 minus theta 2 less than equal to pi, and next case is pi less than theta 1 minus theta 2 less than equal to 2 pi. These three cases come from here. So in the first case, if the theta 1 theta 2 theta 1 minus theta 2 lies between this range, in that case k will be 0. That means minus pi less than theta 1 minus theta 2 less than pi, then k is equal to 0. The next case is when minus pi less than theta 1 minus theta 2 less than equal to 2 pi. That means this is the similar as minus pi less than theta 1 minus theta 2 minus 2 pi less than equal to 0. So here the case in this case the value of k is minus 1, so we are getting minus 1. And next case is when minus pi less than theta 1 minus theta 2 less than pi. In this case the theta here theta 1 minus 0 less than theta 1 minus theta 2 plus pi less 2 pi less than pi, therefore here k is equal to 1. So here the value of k is 1.